Good evening, ladies and gentlemen, guests and participants. My name is A.D. James and I'm an Associate Professor at the University of South Australia and Co-Director of the Southern Hemisphere Space Studies Programme. This programme is an intensive 5-week interdisciplinary, international and intercultural Good evening, ladies and gentlemen, run as a partnership between the University of South Australia and the International Space University, now in its 10th year. So, on behalf of UniSA and ISU, it is my great pleasure to welcome you all to this, the second public event of this year's programme. Before we begin, I would like to acknowledge that the University of South Australia is on the traditional country of the Kaurna people of the Adelaide Plains. We recognise and respect their cultural heritage, beliefs and relationship with the land. And we are acknowledged that they are of continuing importance to the Kaurna people living today. I also extend that respect to Aboriginal peoples from other areas of South Australia and Australia who are present here today and from the lands that you come from. So now I'm very pleased to welcome our distinguished guest speaker for this evening. Dr. Charley Lineweaver, an Associate Professor in the Research School of Astronomy and Astrophysics at the Australian National University in Canberra and convener of the Planetary Science Institute at ANU. He obtained an undergraduate degree in physics from the Ludwig Maximilians Universität in Munich, Germany, and his PhD in astrophysics from the University of California in Berkeley. He was a member of the Cosmic Background Explorer satellite team that discovered the temperature fluctuations. He obtained an undergraduate degree in microwave background. He had research areas and students working in areas of cosmology, exoplanetology, astrobiology, and evolutionary biology. So I'm not going to take up any more of your time, and I'm going to hand you over to Charley. So Charley, it's all over to you now. And thank you for coming this evening.
All right, thank you for that lovely introduction. And I will now share my screen. It'll take me just a second to do this. There we go, and there we go, and share screen. And I should be able to. Now my question is, do you see my screen up in front of you?
Yes, we do. I can see that fine, Charley.
All right, so life in the universe. So I'll be talking about life in the universe and what can life on Earth tell us about life elsewhere. And also I'll be talking about exoplanets and the habitability of exoplanets. This is a big field because so many new planets have been discovered recently. There are up to 4,000 that have been found, and it looks like their planets are everywhere in the universe. And this is something we didn't know 20 years ago. So I'll be talking about two things, one about life and the other about exoplanets. And that helps us give some to focus our thoughts on whether we should or should not expect life elsewhere in the universe. Now, if you have any questions, just put them into the chat and they'll be read out to me. And occasionally I will interrupt myself and say, does anybody have any questions? So this is a picture of part of the universe. And there are about 10 to the 11, that's 100 billion galaxies in the observable universe. I should point out that the entire universe might be, or probably is, spatially infinite. But the part of it that we can see is finite, and there are about 10 to the 11, 100 billion galaxies in it. Now, if you look at a star field in a galaxy, there are about 100 billion stars in our galaxy and in other galaxies as well. Now, so hello, is anybody out there? Now, we can ask ourselves the question, are we the smartest creatures that ever crawled out of the ocean? Or are we the stupidest creatures that ever launched a rocket? How do we compare to other life forms? Will they hurt us? Will they feed us? Yuckity, yuckity, yuckity. Will they eat us? Will they be our friends? Or will they help us join the Federation of Galactic Civilizations? Or will we kill ourselves before they find us? Now, I wanted to point out there's a difference between searching for extraterrestrial intelligence, SETI, and if you need to stay alive, you can just wait for extraterrestrial intelligence. If they're out there, they will find us because presumably they too, or maybe they too have technology and rocket ships and will come visiting us eventually. Maybe there is no one out there. So these are some of the possibilities that you can think of. and I've illustrated them with cartoons. Are we alone? Well, if we step back a little bit and look back at the sun, imagine we can go to a different part of the galaxy and look back at the sun. The sun might be that little star there in front of that right in the center there. And on that sun, around that sun is the Earth, and on Earth, life has evolved. So let's look a little bit more carefully at what has happened. If we start out at the bottom of this slide with the Big Bang, it produces hydrogen and helium. That hydrogen and helium comes together to form stars. The big blue stars have very short lives. They go boom, and they produce carbon, nitrogen, iron, and oxygen, and other elements. Notice the little red stars don't get produced, but they do not evolve. Their ages are older than the age of the universe. For example, the universe is 13.8 billion years old, but those stars can have lifetimes of 30 billion or 40 billion or 50 billion. But our star is one of the more massive ones. It has an age of it will have a total age of about 10 billion years. It's about 5 billion years old, actually 4.567. But on a piece of dirt on debris around our sun, the Earth formed. Out of the Earth, we have life got started, and then we can ask biologists to create lovely phylogenetic trees that tell us how life evolved on Earth. Now, during the 4.5 billion years of life on Earth, astronomy turned into biology through a process that could be called cosmic evolution. And we want to ask the question, has that process of cosmic evolution happened elsewhere? And we also want to know, what can life on Earth tell us about ET, about extraterrestrials? So we can imagine that these stars, excuse me, actually, maybe I should stop there. Does anybody have any questions?
So far, I still didn't see any question on the chat.
Are there any questions about what I've just gone through?
No, there are no questions on the chat.
Okay, I will continue. So this is the picture that we imagine. Some stars will have habitable planets and life will be on them, and some will not. So here's one that has a planet, a habitable star, and here's an uninhabited planet. All right, so moving right along here. So are we alone, and how did we get here? Well, I think the study of how we got here can help us find life elsewhere, because now it's not advancing, please advance. Oh, here. Because the laws of physics and chemistry are the same everywhere in the universe. See, those are Maxwell equations on the left, the periodic table of elements on the right, and those things are universal. We know this because we have tested the physics elsewhere by looking at planets orbiting stars and stars orbiting other stars and stars orbiting other galaxies. And then on the right, we have the periodic table of elements, and we know that's the same everywhere because in the spectra of these stars, we can see the effects of these different elements. We can detect stars and stars orbiting other stars and stars. So of all the hundreds of billions of wet rocky planets, gravity is the same. See, there's Newton's equations on the right. And water behaves the same. That's a lovely wave. Electrons and protons have the same mass and make the same elements and the same molecules with roughly the same relative abundances. These are all universal features of the universe. That's the chemistry and physics. So I guess the main point is that the intimate connections between physics, chemistry, and the biology on Earth should be the same as they are elsewhere. So these are features that are so fundamental that we should expect them to be elsewhere. In other words, there's no terrestrial magic required to form life. That's an essential part of the scientific understanding of what life is. So here's on the left, on this slide, we will see a tree of life. This is called a phylogenetic tree of life. This is the most recent one from 2018. And you can see in the middle, there's a root in red. There are bacteria on the top. There are archaea on the bottom. And eukaryotes are the green wedge there on the lower right. we are a eukaryote. Now, this is a lovely plot. I hope everybody can become familiar with these phylogenetic trees because they encompass all life on Earth. And the point I want to make about this tree is that somewhere at the root, somewhere there, are the places that are the closest to physics and chemistry. Because in a naturalistic understanding of how life gets started, it starts out with chemistry and physics. So that we expect to be common in the universe because physics and chemistry can describe the whole universe, not just on Earth. That is to be contrasted with the following. After 4.5 billion years, we have produced these little branches, the little twigs, all the endpoints, the red dots on this plot, are living forms that are alive today. And they are quirky, like elephants, like people, like sulfur-crested cockatoos, like E. coli. And so I suspect that those quirky things are rare. Now, so another way to illustrate that is, imagine the red dot in the middle is the origin of life. And that's where you have physics and chemistry. And then that physics and chemistry somehow forms life, and that life evolves on other planets. But as it does, it creates a remarkable diversity, but of rare types of diversity. Weird things like naked mole rats and I don't know, eucalyptus trees and daffodils. And the diversity of life is probably some small part of the diversity of life in the universe. That's why it's in the lower right in green. So the basic principle that I think is important to remember is that the closer to the origin of life, the more universal are the life forms. In other words, the first life forms, the most basic ones, are closest to the origin of life, and they are the ones that we should expect elsewhere. And the further from the origin of life, the more quirky are the products of evolution. Now, I want to make sure that is that point I just made does anybody have any questions about that? Because this is a very important point that we can apply to our understanding of life elsewhere, and it can use it to help us predict and guesstimate about life elsewhere. Are there any questions?
It's still no. I have one question. It's about what do you mean by the origins of life?
What do I mean by the origins of life?
Yes.
Okay, so we know a little bit about the origins of life, but not a lot. We think life on, for example, the oldest evidence for life on Earth is about 4 billion years old. So we know that life got started about 4 billion years ago. Now, we also think it was much simpler than the type of life that you see all around us today. And we think, what else do we know? We think it also preferred carbon-12 to carbon-13. That's a little bit of an isotopic evidence for the origin of life. When I talk about the origin of life, we're talking about a phylogenetic tree that leads back to the last universal common ancestor of all life. That's slightly different from the origin of life. So what I mean by the origin of life is the transition from non-life to life that happened on Earth about 4 billion years ago.
So another question is, does bacteria count as a life?
Does bacteria count as life?
Yes.
Of course, yes. Bacteria counts as life. And a lot of people think bacteria is simple, but no, bacteria is already very complicated. The earliest life forms, the earliest fossils we have of life on Earth are stromatolites, and these are bacterial mats. So bacteria that have gotten together and they make a mat, and they can do photosynthesis or other things. And we have evidence of those in the fossil record, 3.5, 3.6, and now even 3.7 billion years ago.
Okay, so far it's just only 2 questions at the moment.
Okay, I'll keep on going then. So the question, are we alone? This is something we want an answer to. But in that question, who is we? What does the word we mean? When I've done a survey around the world, when I ask people, what do you mean by we? Half of them say we humans, and half say, oh no, we, the life on Earth. Now, in this question, if you think we is we humans, then we already know the answer. We are not alone because we're not alone on Earth, and the Earth is part of the universe. So if you ask, are we humans alone in the universe? The answer is no, we're not. But if you ask, are we the life forms on Earth alone? That's a different question. And it's also a different question that also has problems with it because we're not quite sure what life is. I want to give you an example of that. So when I've gone around the world asking biologists, are viruses alive? And here are the answers that I've gotten. 1/4 of the biologists say, no, they're not alive. 1/4 say, yes, they are alive. 1/4 say, I do not know. And another 1/4 says, it's not an important question. So that gives you a sense of the variety of the answers from biologists. And if anybody should know whether something is alive or not, it should be a biologist. And what I'm trying to say is that we don't know what life is. We don't know what the boundaries of life are. The existence of viruses is good evidence that there is no well-defined boundary between life and non-life. Now you could say, oh, wait a minute, that's crazy. I don't believe that. It's easy to recognize life. And I want to tell a little story about this judge here, Potter Stewart. And he said, I know it when I see it. And what he was referring to was hardcore pornography in this, in a film that you can see referenced there in the lower part of the slide. He said, I know it when I see it. And I say, no, you don't. No, it isn't. For example, here is a range of structures. Starting with the top, you have the whole biosphere called Gaia. Then you have an ecosystem. Then you have multicellular organisms. Then you have unicellular organisms like bacteria. Then you have viruses, prions, and even have genes. And so are there size boundaries to life? Now we're comfortable calling life the things in the middle there. You and I are multicellular organisms. We also call bacteria life. But what about Gaia? What about an ecosystem, a forest, or a city even? Are they too big to be alive? Or should we call them life forms? And what about too small? Are viruses life forms? So the whole point is that the word life is associated with the size that we are, and that seems kind of anthropocentric and doesn't sound like the type of objective knowledge that we would like to believe in. The point is that life, the term life, is not well defined. Now, so that was my section on life. Now I want to talk about planets. So in 2012, we published this paper, and the y-axis here is the lower estimates on the percentage of stars with planets. And you can see that those percentages of stars with planets have gone up, up, up. And today it's about 100%. We think if you look up at a star, the statistics tell us that all those stars have planets. We haven't detected those planets yet, but the statistical inference is that they all have some type of planetary system. Now, what about the fraction of stars with terrestrial planets, with rocky planets? And what about the fraction of stars with terrestrial planets in the habitable zone? I should say these are also numbers. They're slightly different. And just to give you an idea of how, I guess, how you can modify the question, we can ask, wait a minute, when you say the word terrestrial planet, what exactly are you talking about? Are you talking about a mass range of 0.9 to 1.1 Earth masses, or 0.8 to 1.2, or 0.5 to 1.5 Earth masses? And also, how narrow is the habitable zone? So, you know, the habitable zone is a planet when you have to get it away from its star, so it's cold enough to have water on the surface, and there's enough pressure to keep that water, to keep the H2O water. And so there's a relatively narrow region, but we don't know how narrow that region is. For example, in our solar system, we think, well, anywhere from Venus's orbit to Mars's orbit could be habitable. but maybe it's only half that wide, or maybe it's only a quarter that wide, maybe it's only a tenth that wide. We have a very difficult time trying to figure out how narrow the habitable zone is. And so to answer the third question on the top, we're not quite sure what a terrestrial planet is, and we're not quite sure how broad the habitable zone is. And those make giving numbers to these questions that make them difficult. So here's one paper that we wrote about 5 years ago. And the answer is that in the red there are on average 2 ± 1 planets in the habitable zone of each star. So that's one answer. And now 5 years later, we have another answer. Here's a paper by Bryson et al. He said there are 0.6 plus 0.7 minus 0.3 rocky planets in the habitable zone per star. And when he was talking about rocky planets, he was talking about rocky planets with a radii between 0.5 and 1.5 Earth radii. So yeah, so does everybody understand what, is there any questions on what a rocky planet is, what a habitable zone is? I want to make sure that everybody understands that there's an ambiguity associated with these terms that make giving quantitative answers difficult.
So far, I didn't see any more question in the chat right now.
Okay. The host, all right. So now, to give you an overview of planets beyond our solar system that we have detected, on the x-axis are the periods of these planets. On the y-axis are the masses of the planets. And you can see here is the Earth, there's Venus, there's Mercury, Mars, Jupiter, Saturn, Uranus, Neptune. That's our solar system. But all these dots are planets around other stars, and they've been detected with a whole slew of different detection techniques that I will talk about. But before I do, this is in 2012, I want to show what happened in 3 years. In 3 years, it went from this plot to this plot. And you can see that there's this giant red cloud of exoplanets that have largely come from the Kepler satellite. And this red cloud has been moving slowly to the right towards Earth because there are lots and lots and lots and lots of planets over here. But I should point out the reason why they're not on this plot is because they are hard to detect. The easy ones to detect are all up here. And so these they're just easy to detect. Why? Because they're massive and because they have short periods. Massive short period planets are easy to detect. The ones down here are almost impossible to detect. They have periods of 10,000, 100,000 days, and their masses are 10 to the minus 4, 1/10,000th the mass of Jupiter down here. So let's talk about how we detect it. How do we know that these planets exist? And I should point out that the Nobel Prize in Physics was given last year for the detection of exoplanets. And the detection technique used was radial velocity. What is that? Well, I have a little movie that shows what radial velocity detection is. So here's the movie. Let's play the movie. It's made by the European Southern Observatory. And here we have a star, and here we have a planet going around the star. And as the planet goes around the star, the spectrum, which is here, of the light from the star is shifted back and forth and back and forth. That shift lets us know that this planet exists. That's the radial velocity technique. Then there's the transit technique. The transit technique, here's another little movie. Here's a star, and excuse me, a planet passes in front, makes the star dimmer, and then it passes beyond it. So we will see the brightness of the star as a function of time. It goes down, and then it goes up again. So we can play that again, maybe. Okay, comes a planet transiting in front of the star. Importantly, we do not see this dark blob passing in front of the star because we cannot see that. We cannot resolve the stars. We just see the stars as points of light whose brightness goes down. No. So those are the two main ways in which we have detected exoplanets. Does anybody have any questions about those two most important ways of detecting exoplanets beyond the solar system?
I think they have some question is about the life is the question is life is determined to be a largely carbon based. If we discover alternative basins, does any of this history and understanding change? And if so, by how much? So the question is like based on the question people were talking.
Well, I didn't understand the entire question. However, part of it was about silicon. And I can answer that. For example, if we looked at the abundance of carbon and the abundance of silicon in the universe, carbon is about 10 times more abundant. And if we imagine that, let's say, the probability of forming life out of carbon is about the same as the probability of forming out of silicon, then there would be 10 times as many life forms based on carbon as on silicon.
So another question is, what do you think the plot would look like when the JWST settles into the orbit?
I'm sorry, what do I think what will look like?
The JWST.
Yeah, JWST is a James. Go ahead.
Into the
Yeah, I think, Charlie, I think the question is, what's your plot going to look like when the JWST is up there? Is it going to give us more information in that plot?
Yeah, the JWST is not a good planet finder. What it can tell us are some of the details of young stars that are forming planetary systems. It's going to tell us about some of the earliest periods in the formation of planetary systems, but it's not going to add much to this plot because it's not built for that. It has a very narrow field of view. It's going to tell us a lot about very, very, very few of these systems. It's not a planet hunter. There are other satellites that will be planet hunters, and they are launched and have been launching and will launch. TESS, for example, is a satellite that has been launched to look at the full sky. It is adding lots and lots of points to that plot, but unfortunately, it's a low-cost mission. It went up very quickly, and so its photometric precision is not as high as Kepler was, and so it's not going to be able to find Earth-like planets around sun-like stars. That is something that Kepler was able to almost do, but TESS will not get there.
Okay, there has two more questions. So regarding the transit techniques, are there other ways that you may see that dip in the star brightness that we might mistake as a resulting from a planet?
Well, yes. As a matter of fact, let me look at my next slide. So we've looked at the radial velocity technique. There's a pulsar timing technique I haven't talked about. We just talked about transit, but there's also something called direct imaging. And these are telescopes that are so precise and have such high angular resolution. They use things called coronagraphs and interferometers that they are able to see directly planets. So let's have a look at this. So here is an image of a star in the middle here that has been blocked out, and these are planets in orbit around that star. And here is a movie of 7 years of looking at this system. So watch me play the movie here. And so you can see those planets going around that star. And so this took 7 years to make this movie, but you can see that these are planets, but they are necessarily very big planets, and this are necessarily very young planets because they have to be shining bright enough to be detectable. And so that's a very small part of the plot that I showed. So we only have maybe half a dozen planets that have been found this way because it is so very difficult, and they only see the most massive and the most distant planets from their stars.
So, Charlie, there has one more question.
Yeah.
To what extent are these methods for the detection complicated by a system with multiple large planets?
They aren't complicated at all. As a matter of fact, if you have more planets, the more planets, the easier they are to detect. It should be so. If when we've detected one planet around a system, it is usually the most massive planet that is closest to the host star. The fact that we have not detected other planets in that system just says, hey, those planets are probably further out and of lower mass. But the more planets there are, the more likely we are to detect something. It does not complicate it makes it easier to detect planets when there are more in the same system.
I have a question. Can I ask?
Yeah, go ahead.
You know, you were saying like, so you were showing that a lot of dots on the planet we don't know. So there might be another humans and other far away planets.
Well, these are planets. Now, I should point out that most of these are not in the habitable zone. And I will show you another plot about which of these are in the habitable zone. I would not jump to the conclusion that there are humans, because I'm sure there aren't. There may be life forms, and as I argued earlier in the talk, those life forms are probably similar to Earth in the sense that they started out very close to biology, close to physics and chemistry, but then quirkily evolved in very weird directions that we have no way of predicting. So I would not bet on there being any humanoids on any of these planets.
Okay.
So here's some debris disk. It's another way to detect planets. And so that debris disk here is in a lovely system. This is a very young system. This is a protoplanetary disk. Planets are forming here and are emptying out this disk and creating these dark bands and the light bands and dark bands and light bands. So this is a planetary system in formation. There's another technique called astrometry, and that's based on the fact that when you have a planet going around a star, it makes the star move. So these swirly digs are the positions of the sun. So 1945, 1947, 1948, 1950, this is what you would see the sun do on the sky if you were looking from far away at the position of the sun. And these movements are due to the motion to Jupiter and Saturn. That's the technique called astrometry. We have not been able to detect any planets that way, but we're just about to with a satellite called the Gaia satellite. That's a very, very high precision astrometry satellite. Now, we can turn these knowledge of the periods of planets into habitable zone because we know the luminosity of the host stars. And we know how far from the host star we have to be in order to have just the right amount of heat or luminosity, kind of like the Earth does. So when we change, so this is the same plot, this is mass of the exoplanets, but now we have, this is the effective temperature of the planet. And we've arrived at this because we know two things. We know how bright the host star is, and we know how far the planet is from the host star. And that gives us the ability to predict very crudely the temperature at the planets. And you can see here that this is the habitable, So this is the habitable, I should not try to do that. This is the habitable zone here. And it is a function of the temperature here. So the Earth is here and Mars is here. Well, this is where they are. Now, interestingly, these planets up here are very massive, but they might have habitable moons on them. Why? Because if they have moons that are big enough, they can hold an atmosphere. And if they have an atmosphere, they can have water. And that H2O will be in water because you're at the right distance from their host stars to have the right temperature. All right. Now, there's another piece of information that we're getting, and that is when we detect a planet, we can detect its mass from the radial velocity technique, and we can detect its radius from the transit technique. And using that, we can plot them on this mass versus radius plot. And here's Earth, and here's Venus, and here's Mars, and here's Mercury. So you can see these are rocky planets, and up here is Saturn and Jupiter. These are gaseous planets. As a matter of fact, we can put the other planets, exoplanets, on this, and we have low density here and high density here. And for example, if you're pure hydrogen, you're right here. If you have water, just water, you're right here. If you're Earth, you're right here. And if you have iron, you're right here. So the point is that there are lots of planets here, and it looks like they may be water worlds. That is, worlds that are not like the Earth. Earth is a rocky planet, but if the Earth were like 2 or 3 times bigger, it might be just covered with so much water that there would be no continents. And then when it got big, they're bigger, you get hydrogen planets like Saturn and Jupiter. So we are, by the data that's remotely detected, we are able to see what is the density of these exoplanets, and then we can make guesses about how many are Earth-like, how many are water worlds, and how many have hydrogen in them like Jupiter and Saturn's, and how many have very, very, very thick and dense, are made out of iron. So this is one way in which we're able to tell the composition of planets from their masses and their radii. Any questions about this plot?
Comment is I have one question. Oh, it's just no question. It's
Okay, so the reason I'm showing you this is because we are making so much progress in our ability to find and characterize exoplanets that not only can we tell which are rocky and which are in the habitable zone, we can also say which are Earth-like and which are Jupiter and Saturn-like. And by this way, we're characterizing all the new planets that we're seeing. And what we're going to do is find the Earth-like ones in the habitable zone, and then look at them very carefully with telescopes like JWST, and hopefully we'll be able to detect their atmospheres, which will then tell us, is that characteristic of life, or is there life on this planet or not? So I just wanted to point out that the ones up here are puffed up like marshmallows, and now this is a different type of plot. This is a different way of presenting planets. Here is insolation. This is how much luminosity is coming from the host star. On the x-axis is escape velocity, how hard it is for gas or a rocket ship to escape. Right here are rocks without atmospheres. The moon is over here, for example. There's the moon. These are all rocks without atmospheres. These are atmospheres without rocks. But right here, we have rocks with atmospheres, and these are the ones we're interested in. And we are getting more and more data. This is a plot from a few years ago, but we now have probably twice as much data on for this plot. And let's see. So here, the low escape velocity, high insolation. And here is high escape velocity, low insolation. And let's look a little bit closer at this. Here's Venus, here's the Earth. Here is the habitable zone here, but I think the habitable zone is really tilted here. The reason it's tilted is because even if you're cold, even if you're down here, if you have a thick atmosphere and you're massive, then your escape velocity is high, you hold more gas, and therefore you get warmer. So I just wanted to give you the impression that we're really making a lot of progress in characterizing these exoplanets and trying to hone in on the ones that are closest to the habitable zone that we know exists somewhere. I should point out that, let's talk about our solar system, for example. Here is a spectrum of Venus, here's a spectrum of Earth, and here's a spectrum of Mars. Notice that Venus and Mars are very similar. They have a deep CO2. Earth has CO2, but also it has ozone. It also has methane. And the complicated nature of this spectra tells us that there is life on Earth. And what we're doing, we will look at other planets to try to see if we can find complicated spectra like this that indicate life on other planets. Here, just to give you another example, here is the composition of Venus. You can see it's carbon dioxide, it's mostly carbon dioxide with some nitrogen. Mars, carbon dioxide with some nitrogen. The original Earth was very much like these two. Lots of carbon dioxide and a little bit of nitrogen. But the Earth now has oxygen in it. All of that oxygen was produced by life forms. The plants that you see outside your window right now, the green chlorophyll, photosynthesizers, oxygenic photosynthesis. And that is something that we will be looking for when we can test the atmospheres of exoplanets, Earth-like atmospheres. I should point out regarding this oxygen, we know quite a bit about the oxygen on Earth. For example, in the first part right here, the first 2 billion years, there was no oxygen on Earth. Then the oxygen rose at called the Great Oxidation Event. And then it stayed pretty high, and then boom, it went up, and here it is today at about 20 or 21%. That is the history of oxygen in our atmosphere. All of the life here did not breathe oxygen, and now here we are breathing oxygen because of this. But again, this is because photosynthetic life, oxygenic photosynthesis, produced this oxygen. And I just wanted to show a last picture of the surface of Venus. We have Soviet missions have been to Venus. They took this picture many decades ago, and Venus looks like it's a place that we'd like to go back to again. But I should point out that it's probably hotter than any oven that you've ever had, and that is a problem. I should also point out that Venus did not start out like this. Venus probably started out more mild, because the sun used to be fainter. About 4 billion years ago, the sun was about 30% less bright than it is today. That's called the faint early sun, and that may have made Venus a more habitable planet, and so it didn't get this hot until maybe after 1 billion years or so. We're not quite sure. But let's see, do I have any other slides? And no, that was the end of my slideshow. So I guess to summarize, I've showed you that we're not quite sure what life is. I've made the point that the origin of the life on Earth is probably closer to what we consider the universal features of life, and therefore the best guesses about life elsewhere. I've showed you exoplanets and the statistics of exoplanets and how we're making lots of progress characterizing those exoplanets. And that progress is enormous. And I would encourage you, if you're at all interested in this science, to get involved in exoplanet missions, because we are finding planets everywhere. There are lots to be seen. The instruments are getting bigger and bigger, and the science cases for these instruments are largely coming from trying to answer the question, are we alone? And any other questions?
So they have a few questions. Could there be a bias in the thinking around the habitable zones whose to say life form cannot live in the extremely temperatures?
Well, the habitable zone is created, excuse me, the habitable zone is essentially a range of luminosities at the surface of a planet, which is compatible with having liquid water. So all life on Earth requires liquid water during some part of its life cycle. And if that's true of life elsewhere, it is certainly a very fundamental part of all life on Earth. If that is true of life elsewhere, then that's why that makes the habitable zone an important criterion for looking for life elsewhere. Does that answer the question?
Yes, but in some ways it does assume a bias that you do need water.
Well, you call it a bias, but I'm not sure it's a bias. The reason why I say this is because hydrogen is by far the most abundant element of the universe. Helium doesn't combine with anything. It's a noble gas, so it does not form any interesting molecules. The next most abundant atom in the universe is oxygen. So H2O is made out of the two most abundant elements in the universe, and therefore it is probably, and I'm almost certain, it is the most abundant triatomic molecule in the universe. And if there are other liquids that are, you can have life, if life is compatible with other liquids, there will be far more of it based on water, simply because of the abundance of water. So it's not really a bias. Let's just say it's a well-informed bias, an educated guess.
Thank you.
So another question is where did the oxygen come from to form the GOE?
The GOE is the Great Oxidation Event. That oxygen was produced by a process called oxygenic photosynthesis. That is, photons from the sun would be absorbed, and then it would split water, and it would split CO2 as well, and that would release oxygen. So the oxygen is released by the splitting of water, and that happens inside of plants.
So they have another question. Is you suggest our solar system habitable zone may be narrower than the Venus to Mars windows, but couldn't it also be wider to Enceladus perhaps?
Yes, that's certainly the case. That's an excellent comment. It could also be wider than that. And for example, there are other problems associated with how wide a habitable zone is. For example, there's something called albedo. Imagine a black planet and a white planet. The black planet absorbs more of the sunlight, and so it will get hotter. A white planet reflects most of the sunlight, and therefore it will not be warmed as much. So albedo is a very important factor in determining where a planet can be and have the right temperature at its surface. Another factor is how many greenhouse gases are in the atmosphere. How thick is an atmosphere? If you have a very, very thick atmosphere, like Venus, for example, let's take Venus with its atmosphere and move it out to where Mars is, or even where the asteroid belt is. Its atmosphere is so thick that 462 Celsius might be a very comfortable 0 or 10 degrees Celsius. So you can really, we really have a poor understanding of how wide this habitable zone is. And so it's not something that you should definitely put in your head.
Oh.
I think he just cut out and left.
Yeah, yeah, unfortunately, we did know we had a technical issue with Charley's laptop, and he was desperately running out of power for the whole program. So I'm afraid we're going to have to end the questions there. And if you have any more questions, we will collect them and pass them on to Charley later. So look, all that's left for me to say really is that, that thank you for the events team and the IT team for putting the event together and making this possible. Thank you for coming. I hope you enjoyed the talk. And finally, this program and the events are not possible without our sponsors. So I would like to thank our sponsors, especially our event sponsors, the Sir Keith and Sir Ross Smith Fund. So thank you very much for everybody coming. And and yes, the event sponsors are now up on the screen, so you can see it in the Zoom as well as on the YouTube video. So thank you to all the participants, and thank you to all of those who are watching the ISU YouTube channel to watch this talk. So thank you very much, and hopefully we'll see you at future SHSSP events. But for now, that's goodbye from us. Thank you very much.